So today's topic is propping and needling. The overall plan, what we're going to cover what propping and needling actually is, and what needs to be considered for propping and needling, and then we're going to run through some different types of propping, some examples, previous designs, and thrown in for good measure. And then towards the end, Richard's going to take us through a more detailed case study of a project in mould in North Wales, and then we're going to go to our Q&A session. So let's start with the Bobby basics, really. What is propping and needling? It's the temporary works associated with creating openings in walls. I usually see these schemes in cut and carve demolition projects where the scope of work is to open up an enclosed area to create a nice open airy space, which is the trend for most contemporary office spaces or high-end commercial and sometimes residential buildings too. And so what we're looking at is how to make an opening in a load-bearing wall. A couple of examples of a typical scope are shown here. And what we have is an existing load-bearing wall, be that of any construction, which is typically masonry or concrete block or concrete. And then the scope is to open up the wall, but we need to understand what this wall is doing in the first place, and then the loadings that it currently is supporting, because this is really going to be important to provide the support in the temporary term. So why can't you just knock the wall down and whack a beam in? Well, the reason that a beam is usually installed is to support the structure above, and then the structure could include, say, a wall, floors, beams, roof, arches, anything like that. And the typical loading triangle onto a beam of a lintel or a lintel is shown here. So all the loading within that 45-degree load triangle is taken by that beam. And then in addition to this, half of any point load or distributed load within that 60-degree zone is carried by the beam too. And this could be a window opening or a floor load or roof, for example. And then we've got an extract here from Fiona Cobb's very good book called The Structural Engineer's Pocketbook. It's a fantastic book, and every engineer should have one of these, in my opinion. But you can see all the loading from the floor and the wall within that 45-degree zone is taken fully. And then a half of any of that applied load, but not the self-weight, is taken too as well, not the wall self-weight. And this model relies on the wall above arching over that opening, which is shown here. So for larger openings or openings where there's not enough masonry around to support and enable this mechanism, so in those kind of areas, this method doesn't really apply. In which case, the full loading above the opening should then be taken and not that 45-degree loading type shown here. And it's worth noting that this is because the arching effect, which is why very small openings or services or ducts, that they don't require any support usually. And when you start to get to larger openings, say above half a metre or so, some form of support may be necessary. So let's look now at the type of things that we need to consider when we are propping and needling. The importance of site investigation. It's absolutely critical that we know what the structure is and how it's currently behaving so that we can predict what's going to happen once we start mucking around with it. And that comes down to GIGO, the garbage in and garbage out. If the idea of the solution is based on a load of rubbish, then the solution itself is also going to be a load of rubbish. Proper site investigation is required, and a little thought and money spent at this stage is really going to make for the much better solution later on, the correct solution later on. Next one is lateral stability. Before the wall is removed, the lateral stability of the propping and the wall itself will need to be considered. It's very important. The support of other structures and not just the wall in question. So don't forget that adjacent floors may need to support, they may need support to then enable you to remove that wall or the live load, to remove the live load from the wall as well to reduce some of that loading. Or if the wall is providing some other kind of support other than vertical, so for lateral stability or bracing, then that needs to be taken into account as well. The whole sequence of construction needs to be considered and not just the propping. This is really important for a couple of reasons. The first being loading of the temporary work. So the system needs to be designed for the worst case loading. Therefore, if the structure will be loaded by plant or material storage or snow or potential vehicle strikes during its design life and not just at the time of installation, then this needs to be considered at the design stage. And the other one is to do with load history. And this is a phenomena that will include how to put the loading back into the permanent works once the propping has done its job. Another one is what the permanent works is going to look like. If we plan in advance and we understand what the permanent works is and how it interacts with the structure, then it may be that we can incorporate the temporary works into the permanent works and make a very slick and efficient and buildable solution and potentially eliminate any temporary works. Are there any services in the walls nearby? Are any exclusion zones of note that we need to consider or that we need to put in? The foundations for the proposed propping. This is important as settlement under the prop foundation will lead to potentially unsuitable support for the wall. How will the new permanent works be installed and what's the plan of installation? Is it being installed with a genie lift and how wide is that? Or do we need a crane and a pocket in the slab above with the tower crane or something like that? We need to know that to enable us to design a suitable solution there. We need to understand the constraints and the limits of the structure. So we need to know the allowable deflection on the structure during the works. There will be some movement. Any openings in load-bearing walls will lead to some movement. Often it's just some micro cracking if we've got lots of supports in there. But we need to know what kind of movement limit is permitted and essentially how much is too much movement. The loadings that must be considered, are they all coming from above, or are they point loadings, or are they evenly distributed? And then finally, the overall stability of the structure. Who's taking responsibility for that? And also, what about the sequence of other openings being made and the interface between them? This should be coordinated by the site team or the temporary works coordinator, make sure that the design solution, the engineered solution, takes into account that there are other openings and holes in the structure at the time when this activity is being carried out. And then finally, you need to ask yourself, is this solution buildable? It's really important that from the design, from both the permanent works and the temporary works, is buildable and suitably mitigates risk using the ERIC principle of eliminate, reduce, inform, and control. That hierarchical control of risk. Openings in load-bearing walls and structures can go seriously wrong if not carried out correctly. So the overall solution must be safe and the sequence of construction must be practical and buildable. So let's use this example that I've got here to explore some of these points. So I've illustrated here the current loadings that would be acting onto this wall. So we've got some from the floor above being distributed down through around an opening. We've also got some loading coming in from an arch from the right-hand side and then from the load-bearing structures above coming down that wall as well. So if we go through our list that I've put down the right-hand side, site investigation. So here we'd be interested in wall thickness, the layout of the structure, including floor spans and floor-to-ceiling heights, the floor construction, so we can work out how heavy that is and what it's made out of. That's really going to be important for to determine what the loading is on our props, which leads us to back propping. So if we've got the loading from our props, then what are the props going to be sitting on? Is it feasible to back prop below? The floor below may be occupied by a third party. So we need to know those kind of things. Lateral stability and support of other structures. So we've got an arch here. And will that be supported by the needling, or is the wall acting as a shear wall to provide stability to the whole structure? Construction sequence and how the new beam is installed. So what's the permitted working space? Is there a specific construction sequence required due to particular site constraints? The permanent solution as well, that feeds into it. So what is it and what does it look like? Does it consider that the temporary works will need to be used to install the beam? And believe me, that does happen where you have very, very tight constraints, which leaves you no room for temporary works. And it requires some coordination between the permanent works engineer and the temporary works engineer, as well as the site team, to make sure that we get something that's buildable in there. Check of any services. Are there any services, and are they live, or do they need redirecting, supporting in the temporary term, which may require its own particular type of propping. Exclusion zones. So are there any localized exclusion zones that are required, or can there be during the propping installation to reduce loading on the partially demolished structure? That comes back to that ERIC principle of hierarchical risk control. If we can have exclusion zones, then and eliminate the risk of people working or operating above this structure when it's temporarily supported, then we should be doing that if possible. Allowable deflections on the structure. So that's really governed by the type of structure and its use. It's really important, as it often is the driving load case for the design, how much movement, how much deflection that is permitted in that span. Are we supporting the vertical loadings only? This links back to the arch. Do we need to provide some horizontal support to this arch, perhaps? And then overall stability of the structure with the openings created. So if this wall is acting as a shear wall of some description, then a global stability assessment may well be necessary because we're cutting a big hole in it. There should be somebody reviewing this, whether you can turn the structure into that Swiss cheese that I was talking about earlier with all holes in it, and can they all be completed at once? Other openings nearby and the interface between them. So that last point really links to this as well. So we've got the global stability. On some schemes, we may well stipulate that openings are carried out or completed floor by floor to mitigate that risk of global instability. But that really comes as its own item, really. So we're not just looking at these as independents. We're looking at them as from a holistic view. And this list isn't exhaustive. There are other considerations that will be project specific. So if you plan ahead and get engineering input on the design at an early stage, then the work should go really nicely. Okay, so now that we know all the things that we should be considering for our propping and needling opening, it's time to furnish our imaginary toolbox with a number of potential solutions that we've got up our sleeve that we can then utilize for our project. So that way, when a particular situation comes up, we can run through those various types in our head and think, okay, well, that's the best solution, or well, this would work better here. So as shown here, we've got a list of several different types of propping and needling schemes that we can employ. Sometimes it's a mix between them, which is most appropriate, depending on the project. But we're going to look at the 7 today, which I feel are the most common. Okay. First of all, we're going to start with some smaller openings that are more common in like typical domestic applications or domestic type work. And we're talking maximum wall thickness of around a brick thick, so 230 or double skin cavity wall, with openings up to around 2.5 meters or so. So the first example that I've shown here is a no more prop solution or temporary lintel. It's a quite a clever little piece of kit, proprietary, off the shelf, and it replaces the need for multiple acros, saving site prep and time, particularly useful on upper floor work. Yeah, like I say, it's an off-the-shelf product, great for small scale applications. It does rely on the masonry arching though, which we can't be applied in all situations, like in corners and near openings, but quite a neat little solution there. Similar to that solution is a what's called a brick brace. That's a clever system. It uses essentially uses the technology of like a post-tension structure. So what we've got here is a scaffold tube which runs across the top of the opening, and then there's special clips which connects onto that scaffold tube, and they are inserted into the vertical masonry joints. And then in there's 2 plates, which then when you tighten those bolts, which are on the side, they start to open out, okay? And as they open out, they put that bottom into compression. So they push out, they push the bricks out and kind of create that big compression in the bottom there. Then when you open up the brickwork underneath, then it acts the wall above as well as that kind of compression strip at the bottom, then remains in compression because it's kind of been pre-tensioned up. It's a pretty clever system. It's not something I've used, I've specified it, and then it wasn't quite suitable for that application. So it's something I haven't used, but it's quite a handy solution that yeah, for that more domestic scale. And on the right hand side there, I've put in, you can see the difference between a this brick brace design, which is quite neat, and then some macros. And I feel as though that picture is a little bit unfair, considering that one is quite a mess with the acros, and the one that of their brick brace is very clean. But you know, it gives you a bit of a comparison there. Okay, now for strong boys. So these are props that are of similar application as the No More prop solution, in terms that it uses the prop head attachment and that's inserted into the wall. And then this prop head is good for about 350 kg. So we're talking small scale here. What we do here is we've got a steel plate which we cut into the wall at regular centers and support the brickwork. An example of this propping is shown here. And a row of props closest to the wall has the head attachment, and then the row of props just further away from the wall is then supporting the floor above to remove some loading away from that opening, keep that loading down and under 350 kg per prop. And then the propping itself was then founded on some aluminium beams that spanned over the floor and put the loading back onto some load-bearing walls, because we had a weaker floor in that location. And we've got this concept illustrated here. So on the left, we've got a very simple scheme where the props are supported on the floors, and to the right, we've got a weaker floor alternative, which was the photos of that previous slide. Most often, the loadings that we get from strong boy props are pretty low due to their low capacity. So propping down to an elevated floor is usually acceptable, providing that a proper assessment has been carried out. But understanding that floor spans and the construction of the floors, that's the critical part, and links back to that good site investigation in the first place. It's a good system as the props are all on one side with that plate. So the other side can be used for access for that lintel installation. So if we review just a typical sequence of that lintel installation, so we have the propping installed, and then fully supporting the load. And once we're happy with that and that gets signed off, then the opening is made to receive the new lintel or the new beam. And just note that that doesn't have to be the whole wall, top to bottom. It just needs to be a slot that's big enough to allow the beam and the pad stones to be installed. And usually it's quite helpful just to leave it at that slot. So when you get your beam in, you can just rest it on some packers on that on the top of the wall, as opposed to having it suspended in the air. Once that beam is installed and the pad stones are all good and it's dry packed, it's ready to take the load then. And at that point, once we're happy with it and it's load bearing, then the temporary support can be removed, and then the remainder of the wall can be removed and demolished. And that's the process in a nutshell, really. Another example of that system here, and you can see we've got some bracing in there. It's quite a neat solution and looks just like the drawing. So that's the kind of thing we want to see. Okay, so now onto some more larger loadings, some larger openings, and therefore we need some larger props. So it could be a thicker wall or higher floor loadings or something similar. So we've got the needles at regular centers going through the wall that you can see there, and then that needle is supported by a couple of props each side, which then span down to some kind of foundation, whether that's a raised floor, which is good for the load, or whether it's a ground bearing slab. And the load kind of follows down the wall through the needles and then down the props and into the ground. We've got some horizontal bracing there just to provide stability, to make sure that the needles don't kind of act as a sway frame and move. That's the general concept. An alternative to having a needle on every prop is to use a header beam between these props and then support your needles from those. So then you need less vertical props. So the centers of the needles remain the same, which is important to ensure support to the wall, but then you have a larger opening beneath, which can assist in construction and access. And so we've got that solution shown here. And then we can see on the right-hand side there, we've got a raking prop tied down to a little pad, which provides that lateral stability, which is important. If the wall is losing some of its stability in that direction, if there's a floor directly above it or something where the wall's tied in, then it can be proven that the wall doesn't need to provide, or the props don't need to provide stability. But in this case, as the next floor, the next horizontal tie to that wall was a fair way up, then we had a raking prop on there for good measure. If we're propping an opening on a raised floor and the floors are weak, so for example, like a timber floor or something like that, then a reverse needling scheme can be used, which is what was shown here. So this scheme takes the load from the wall, it distributes it into the top needles, then it comes down into the props, then back into the lower needles, and then back in the wall, and it works just like that, okay? So that's a really great idea because the load path remains unchanged from the floor above to the floor below, which mitigates the risks associated with mucking around with load paths of a structure and into floors and back into walls. Here, we're just kind of bypassing an area of the wall and then passing that load further down the wall so that we can create our opening. So the propping from the floor to the ceiling here is used so that there's something to brace back to for lateral stability. And a tall prop such as this is not required on every prop, it's just on a few, so that the props can be braced back, and we've got something to build from as well. It helps with the constructability. So if you've got very tall ceilings, then propping like shown becomes quite difficult. So we can use scaffold rakers or something like that. It's essentially just to provide some support. But this reverse needling scheme is really quite helpful on the weaker floors or where you want to separate particular activities between floors so that there's no back propping going all the way down the structure and then limiting access and limiting site construction activities on those floors. As a little break from those schemes, I just thought I'd show you some kind of some bad practice, I suppose, of accurate propping and needling. So this is a project where we had no involvement in until we got called out once it was identified that things weren't going very well at all, and it was a domestic builder essentially who was way out of their depth. So the wall is basically falling down here and the floor above is unsupported. There's no bracing to the props that you can see. Also, there's no positive connection between the prop heads and the lintel, whether that be we usually detail U-heads at the top of the props to make sure that they can't shift or slide off, or some positive like mechanical fixings. But you can see there that that needling scheme basically isn't doing anything. And then the foundation is on a raised floor. So they did consider that may need some load spreading with some timbers, but this was certainly not good practice in this case because the timber should really be concentrated in the zone here, whereas they've just laid out some 2x4s or something like that in that zone, and most of them aren't doing anything at all. If there was enough timber to do a double stack, then that would go a much better way to providing that additional support and load spread. But looking at that, I don't think the props are doing an awful lot anyway, so that was questionable, and what kind of loading that was going onto the floor in the first place. So anyway, just a little nugget of bad practice, which is quite amusing to see sometimes. Okay, so on to our next one. Let's look at needling with larger beams with a pinned wall. This was a scheme where the loads were really high because we were supporting a significant amount of the whole facade on this this front elevation. The area beneath the propping was also required to remain very open to enable the demolition works, which were quite complex. Therefore, we developed a scheme that had props at 5-meter centres, and then the larger needles, which were at 2.5-meter centres. And then it had some back-to-back PFCs spanning between the needles, which were there to pick up the load from the wall. The PFCs were essentially strengthening that bottom line of the wall, and they were designed to span between those larger needles. A sleeved rod was put through the wall so that that would tie the PFCs together, and we can see a close-up of that here. Of those, that's a close-up of those back-to-back PFCs with a rod through in the middle. And that sleeve is really important because the rods themselves, they don't have have got a very low bending capacity. Like they don't really like bending the all threaded rod like that. So having a sleeve in there means that the CHS section, which we use as a sleeve, could take that shear loading and bending loading that you'd get from the thick wall. And then due to the size of the loadings and the quite awkward site constraints, it was necessary to go with a bespoke fabricated solution. And this PFC pin solution also could be used to limit the amount of damage in the wall for more, because a more traditional approach of having needles at much regular centers would have led to larger openings in the quite fancy stonework wall. So this is a solution which worked very well for this project. It was quite a number of constraints which led to the solution. And okay, number 5, we've got the Pinafore stool method here. It's a method of casting an in situ beam into a wall over a proposed opening. The illustration shown here has been taken straight from the Temporary Works Toolkit, which is a publication by the iStructE, and this is part 10. But there's a series of articles aimed primarily at assisting permanent works engineers with temporary works issues. And there's one on propping and needling, which is really quite good. So the sequence here is to break out the pockets in the wall and insert some stools, which are usually steel. And then once these stools are in and dry packed, i.e. ready to take the load from above because the support is tight, and then the lintel channel is formed. And into this channel, we can slot rebar, and then the new lintel is kind of placed. So we've got the shutters that are placed around the slot, and then the concrete is then cast, and the top beam then must be dry packed at the wall soffit to make sure that it's bearing and it's properly taking the load, and there are no air pockets as the at the top through the casting process. And then once that concrete is cured sufficiently, then the wall below can be broken out, and then hey presto, you've got your opening created. And those stools are cast in and therefore redundant. But we've got an example here where we've used this method during a low cross project in East London, part of the Crossrail project. We used steel stools here that were designed to sit inside the new lintel and then not clash with the reinforced concrete beam reinforcement. And the process was we make the pockets, install the stools, then we form the slot, we insert the rebar and cast the concrete. And once that's cured, then we can make our opening underneath. It's a very, very neat solution. This is a detailed view of that stool interface with the reinforcement that we specifically designed these stools so that they wouldn't clash with the permanent works. Yeah, and it worked very well, and I've used it on other schemes since. It's quite a niche method, but it's one that's very handy to keep in mind because for certain projects it's yeah, it fits just right, and it's certainly one to keep in mind. Okay, on to the next one. So similar to the Pinafore stool method, we've got another one which is a system which utilizes stools. And here's where we use back-to-back PFC stools that then allow the installation of precast lintels. So those channels, those PFC parallel flange channels, are the perfect shape to enable the installation of those lintels, and then the wall is then removed, and that's all installed and ready to take the load. So if you look at a typical opening we've got here, you can see that the load interaction zone and the proposed location of the stools, which are those 3 hatched blocks. So if we take a section through this, we can see the sequence of construction. So the sequence is similar to the Pinafore stools method. However, as this is a sequence that allows multiple lintels to be installed side by side, one side is usually completed before the other to ensure that the wall receives as much support as possible throughout the work. So here's what we do. So we break out pockets. So it's a careful a breakout of a pocket and then installing the stools on one side only. Then we dry pack the stools. Then we can form a slot along one side and then install a lintel. Then we dry pack that lintel, and then that's ready to take the load of one side of the wall. And next we do the same on the other side of the wall until we have the full support along the wall, at which point the TWC signs off the installation and permits the wall to be removed. It's again quite a niche solution, requires specific site or construction of walls, and the permanent works to be installed needs to be able to be installed in stages like that. But it's one to keep in mind. It's very helpful solution indeed. Okay, And to number 7, which is scissor propping, and that leads us to our a bit more of a detailed case study on the India building in Liverpool. So this project, it was within the India buildings in Liverpool, which were constructed around 1931 and then being replaced in I think it was the mid 1800s. Then it was originally constructed. But the structure essentially consists of a double-story basement and steel frame supporting some filler joist floors. It was grade 2 listed, and it was really quite lovely inside with some really nice features. So the overall scope of the project was to redevelop the structure, which included a cut and carve type demolition and strengthening works. So the cut and carve type scope meant that there were numerous floors and wall openings. So as such, there were many different systems of needling and propping used. So I'm going to focus on a particular area now, which is the scissor propping. So the design brief for this particular part was to create an opening to the new lift shaft, which was being constructed. The existing floors on either side of the opening were also not the same height, which added to further complexity. And there were also some embedded steels within the wall as well. And then due to this construction work, it was agreed that the best option to go with, because we produced a number of different concepts, was the needling scheme from one side, so from a single side of the wall, which had detached this activity from the lift shaft steelwork erection, which is going on the other side, and effectively removed the link between the two activities, thus kind of breaking that critical path and allowing two different gangs to just carry on with their own part of the project in a very close area independently. So we've got the solution here and a overview of the scissor propping. So you can see on the bottom left of the screen, this is a very rudimentary sketch that I've done. And essentially what it does is from one side of the building or one side of the wall where the load comes down, it gets transferred into a needle. Then it goes down into that first prop and then it gets transferred into the lower needle and then back into the wall below. So it's similar to the reverse needling concept. But because we've got a cantilevering needle at the top, we need to have some kind of tension tie at the back, which then provides that that resistance of to that top and bottom needling. And that's why it's called the scissor propping, because you've got the kind of tips of the scissor poking into the wall as cantilevers and providing that support. So on this particular project, we utilised this solution and we used a proprietary kit, maybe System 160, which provided a very robust frame that could be used to take the quite large loadings from the structure from above. There was an existing opening within the structure that we allowed for. You can see we've got where that white box out is on that top elevation. So we put a prop there and a little spreader at the base so we could transfer that load. It's also important to think about the installation and how the new structure is going to be installed. And so in this case, the allowance was made to install the new lintel with a genie lift. And so we had to make sure that the opening in the middle was wide enough so you could get the genie lift forks through. Maintaining the load path was a kind of key to this concept, so that we didn't have any back propping down through below the structure, because I think below this structure was a very tall ceiling, and then below that was some vaults, so very difficult to access. So we wanted to maintain that load path and distribute it back into the wall within that same floor. And then finally, again, the system enabled the work to continue with the new lift shaft on the other side of the wall. So that allowed for savings on program, enabling both those activities to progress independently. And here we've got the solution in reality. So you can see there we've got a number of holes in the wall where we fit the needles, and it's important to have that back prop at the back that loads the floor really from the propping self-weight. That enables the thing to be built, and when it starts taking load, then the load is transferred into the wall where the needles are. Yeah, quite a neat solution on this particular part of the project, and it helped the project team out no end, because you can see some of the steel work on that photo on the left. You can see the lift shaft behind and some of the steel work going up, so it meant that these activities could be separated out. And that's the general common types of needling and propping that you'll see. So I think I'll hand over to Richie now, who's going to take us through a case study on mold, where we can see some of those in action. So over to you, Richard.
Oh, thanks, Josh. Yeah, I'm just going to talk about some of the work we helped design for the theatre in Mold in Northern Wales. We're working for a company called Fibram, and they did a fantastic job of getting us in early and getting us to actually discuss everything very early doors so that before they even started doing the work, we were there and we had an idea of what's going on. But just to give you a background on the building first, it is a theatre, Northern Wales, Grade 2 listed buildings built in the mid-90s. That's 1990s, not Josh's 1830s, which is more impressive. But for this, they were just modernising the building, carrying out some much-needed repairs and adding on a extension to the front and a bigger extension at the back so that they had more room for practice rooms and rehearsals and things like that. But like Josh's one, we were doing a cut and carve scheme on this. And if you can't really see all the red lines, but most of the walls in the top left section were coming out. The walls, roofs and areas, large swaths of walls coming out in the bottom right as well, and a tower coming out in the bottom middle there. And instead of removing huge aspects of the whole building, the whole top left section, the cut and carve system means that you can replace actual small aspects like individual walls instead of full demolition happening. But that's where the more technical propping that Josh has been talking about comes into play. And so we can move on and look at some of the propping that we actually got to put together. So this is one of the designs for propping that we actually did. You can see that it is one of the more basic propping designs. We were just taking out a line of walls that's in the middle of the building on the top floor. So it's just line of props lined up to take the floor load so that removing the wall doesn't disrupt the load path of the wall coming down. And if you click one more time, Josh, you can see that that is one of the walls that we had taken out, and then that slab just spans between the props instead of spanning to the wall and then spanning to the next wall. And this is a bit like before, but the wall was much longer, and you can see that it's a external wall as well instead of one of the internal walls in the building. So this was at the south end of the building next to the tower that was coming out as well. So because the tower was coming out and we had a long line of propping, an important thing to note was that we would have a lot of lateral loads in the props, so wind loads, and you weren't getting stability from the tower anymore. So what we did is we triangulated the props here. It's a very easy system to add on to a line of props that we're putting in. So all you do is triangulate it back, and then that gives it a lot more stability to resist wind loads and any lateral loads that were occurring in this roof. So as Josh said, as you get more complicated, you need to think about the whole building rather than just one small aspect of it. So in this case, we weren't just removing one wall, we're removing an entire section of wall so that they could be replaced with a new building that was going in and corridors going in. But in this case, you can see that I use a system much like one that Josh showed off earlier. You've got the strong boys going into the wall and then props holding up the floor. But the trick with that is because we're doing on every floor, the loads accumulate as you go down, and the propping at the bottom, they're actually Titan props at the bottom rather than acro props for the other floors, because the load gets added on each floor. So after that, the loads at the bottom get quite large, so the floors wouldn't be able to take it. So there's some nice foundations at the bottom there as well that we added in to the plant. And this is a not so simple aspect of the propping. You can see we're taking out that red wall in the picture there, and that had many different complications to deal with in the propping. So you have 4 different floor arrangements. You have a north to south floor arrangement in the top left, and then at the bottom left it goes from east to west, and then between the green beam and the red beam it goes east west, and then beyond that it goes north south. And then just to add in more complications, there's a curved wall at the top as well, and then on the floor above there's a curved walls that's sitting on the floor and the wall that's coming out. So propping this was a lot more tricky than a normal propping job, but as you can see, we had to prop different orientations, and instead of propping the floor, we propped the beams in a lot of places. But to leave enough space for the work to actually be carried out, that line of Titan props all had to leave a gap so that workers could actually get in and demolish that wall. And then the bracing in between all these props had to be removable one bay at a time as well, which added even more complications when the floor above had curved walls on it with odd load paths all going through it. Fortunately, in this case, the red wall also had a beam at the top of it, which helped the scenario, and a column was kept in the middle as part of the temporary works to help facilitate all these walls coming out and all this propping going on. And while we were doing this propping, it was very important to understand what was going on in the entire building around this area, not just looking at one wall at a time. So looking at this level, looking at the level above, looking at the level below, to make sure that all these props worked. So that was a very complicated one. Now we go in the other direction where you don't need huge amounts of props. Instead of propping an entire line of props along these 2 beams that are in the blue and the green here, all we did was put in a Titan tower at a well-positioned angle to take the loads from both of these beams, and then that column that you can see at the side, well, see at the side of that picture, can come out very easily once those Titan props are in. And then because you didn't use so many props, you've got a large, clear, open space where you can get on with all your other works, as Josh did at the India building. You can have props in, and that was the roof being replaced behind these props. So if you had a line of props going through that, it would have been very awkward to replace a roof. And then if you move on, Josh, sometimes simple is better, but sometimes no props at all is better. So this was the fantastic early engagement we were talking about earlier. Instead of propping all these roof beams that you can see here, what we did is we kept in stubs of the walls at the end to still support these roof beams. But we were able to facilitate it so the permanent works would be installed before these stub walls had to be taken out. And then you can get in the permanent works to support these roof beams before you go to the hassle of taking this out, and you don't need to prop it at all. So providing it's safe, sometimes the best way to prop is to not have any props in at all, which I'm sure Josh would agree emphatically about sometimes.
Yeah, that's our mantra of sometimes no temporary works is the best temporary works, which doesn't mean that if you need to put a prop in, you don't put the thing in. But it's this, if you can coordinate and be smarter and plan ahead, then you do away with your props, do away with the temporary works, and speed up your program. So yeah, it's a great example of that.
And that's why it's good to have good relationships with contractors who get you in, because they get you in early and they know better. And now I'm moving on to some needling. Now, the extent of the needling at Mould was everywhere. There was needling on every second wall and throughout the building, just because they were rearranging all the corridors and making new rooms everywhere. So what we had is, you might notice, these are very similar to the designs Josh was showing off earlier, where you just have the simple needles going through the wall and you leave enough space to install the lintels at the top, and then you can create your opening quite easily. Sometimes, though, you need bigger needles going in, and I had a wee speech done for reverse needling, but I think Josh stole it verbatim and stole my thunder completely. Thanks, Josh.
Sorry, mate. Yeah, we feel free to go through it again on this particular scheme.
Oh no, it's the exact same thing that you went through earlier. Instead of having the load coming through the wall and then changing the load path, you have it coming through the wall into your needles, into the props, and then back into the wall. And that's reverse needling at its best when you can keep the load path from floor to floor instead of changing around. And I think all over, what we did at Mold was very useful, and because we had such early engagement, we could help them with a lot of things. So we could do demolition sequences for them, and we could get all the propping. There's a plant assessments that needed done, and again, that's the best propping is no propping when you can get plant to work on floor levels themselves. But sometimes propping is needed, and so we have lines of props where they're needed to remove walls. And in other areas, we created openings in the walls and had more propping there. If you just keep on clicking, you can see some of the larger propping schemes we did on this site. Lots of props going in. You can see a red wall that we removed completely. And that was all the fun and games. And you have to remember to take into account the grand scheme that even though you're making openings on the first floor, it doesn't mean you don't need to back prop on the ground floor to make sure the load paths are correct and the floors can take all the loadings. And I think at that, I'll pass it back to you, Josh.
Thanks, Richie. That really concludes the presentation today. So if you'd like to know a little bit more about the subject, there is lots of information out there. There's a whole chapter on propping and needling, for example, in the Temporary Works Principles book, which is the ICE publication with the yellow bands you can see on the screen there. But then there's lots of other helpful documents and information. There's a wealth of knowledge on the Temporary Works Forum. BS 5975 itself is the kind of the go-to British standard for temporary works. A lot of good information in there. There's some good building guides as well in provided by the BRE, which are very helpful, similar to the Temporary Works Toolkit, which is a publication by the iStructi. And yes, there's plenty out there which on the subject and some examples.